Welcome back. Nice to have you all back. We are now starting our next session, Artificial Intelligence at the Edge. Stephan Karmann is the chairman of this session. He's responsible for business development at Hahn Schickard. He will receive all your questions and ask them to the speakers in the questions and answers panel at the end of the session. And now I'm pleased to hand over to our first speaker, Heiko Claussen. He is head of autonomous machines at Siemens and will talk about industrial robot grasping and deep learning. Here you are, Mr. Claussen.
Hello, welcome. All right, today I would like to talk about how we can bring artificial intelligence into the shop floor, actually into the logic controller. And I will use an application, industrial robot grasping, for this use case and how this is basically being used in the PLC. All right, so at Siemens we cover different areas in the going from the cloud to the edge and down to the controller. And each of them bring particular value also in the AI space, and we have offerings in all of this. I mean, you can imagine in the cloud, you can train large amounts of with large amounts of data models. Then you can distribute it on edge systems. This edge management then allows you a flexible management of your overall systems in the field. And then in the control layer, you focus particularly on real-time aspects. You have high data rates coming directly to your systems, and you want to make real-time decisions affecting the control of a machine. And today we will focus on this offering and the applications in this space, because it really, in an essence, brings the value of AI onto the shop floor. An offering that we have there is a so-called technology module that has an hardware-accelerated deep learning processor in there from Intel, and Movidius X chip. This is a very efficient accelerator for deep learning. It's about 2 orders of magnitude more efficient than a CPU for such applications. And we have this tightly integrated in this way in the control layer. So this technology module is connected through a backplane bus to the controller, to the PLC. So it's a ladder logic-based PLC, for example. It can also be a software controller. And in this way, has a real-time connectivity to this deep learning accelerator. Here we can input high bandwidth data, like for example through a USB 3.1 or Ethernet. For example, you can connect any gigabit Ethernet vision camera to this device, stream high-speed video streams or time series data onto this accelerator. You have then your deep learning models onto the accelerator that is extracting the smart information from this high bandwidth data, and then provides this decision in real time to the controller that can make real-time control decision based on this. The training of the models is provided through standard frameworks, like for example Caffe2 or TensorFlow, and that is basically just being compiled and combined with an application program on an SD card, which acts as the local storage for this device. Given this design, you don't only get the real-time capabilities, but you also have the possibility to scale this. So, the loading of the CPU on the PLC is minimal. Therefore, you can have many of these modules on one standard PLC without loading the current CPU. That also allows you to update brownfield devices without having to worry that you bring down the application that is currently running, because adding such a module only loads the controller as if you would load it with a standard additional input-output module. So you can have, for example, 64 of these modules onto one simple ladder logic-based system. Also, these are all industrial hardened. and can be also set in a distributed setting, so you can combine them with communication modules and distribute them over the plant. As I said, industrial hardened and robust to the temperature and vibration environments that you usually find in the industry, as well as the availability, long-term availability, and other aspects of an industrial setting. The applications for such acceleration is pretty wide. As I said, here you see, for example, a distributed setup where you can then, for example, address applications in the industry like visual quality control, which, for example, detects if a produced part has any faults, or if, in this case, a flame in a furnace has the right shape or color distribution, many other things in different domains for visual quality control. You also have time series analytics, like your standard process monitoring, process optimization. You have aspects like real-time optimization based on high-speed data that you can connect in here, and other more advanced technology aspects that you can enable, like advanced robotics in this domain. You are robust against external influences. It's very integrated, and you can enable complex neural network architectures to be operating right at the edge, right where your device is close to the machine. We're focusing today on the robotic topics with the application, so to show what really capabilities enable in an industrial settings here. While you can, train these neural networks based on data offline and then deploy it on the hardware, on the TMNPU here, this also enables you architectures where you can continuously update based on data that you're recording on the shop floor. And this is an architecture that is highlighted here that would enable such an application. You would, for example, gather the data on the controller, send it to an edge device over, for example, the Ethernet communication, then either train it there or in the cloud or in a fog kind of setting, and play it back onto the TMNPU with a new model architecture that can then be run. And you can continuously improve this so that you have a continuous learning system at the edge, while having the low power, passively cooled footprint that is required in many industrial applications. At Siemens, we are addressing a large and broad set of application areas. Here's a display of the different verticals that we are addressing, going from the process industries like oil and gas, over hybrid industries like, for example, food and beverage, towards discrete industries like automotive. Today, I'll focus on an application in the interlogistics space. Here again, this vertical is segmented in many different applications, but we will only focus on the mobile robot and picking application. In flexible picking, there is already a lot in the market for robotics and picking, as you are probably aware. And the traditional approaches, though, focus on standard machine learning. So this is on the bottom here. You generally know which parts you are picking, and you have the CAD model for that, and you have there's a particular mature technologies to detect features based on this. If you're talking about 4 degrees of freedom, but it's still a challenging problem for fully complex 6 degrees of freedom unstructured problems. Challenges here are that it still takes a lot of effort if you have a large variety of objects. because you have to train for each of these objects the pick points. You have to define the pick point label, and and it's generally requiring expensive, high costs vision. The focus that we want to highlight today is flexible picking, what you show on the top here. The focus is, as I said, picking of unknown objects. So if you're like in the logistics space, you have millions of different parts that are constantly changing. You want to pick them without having this knowledge about the CAD model autonomously. So this is enabled with deep learning and deployed on this hardware that I just introduced before. And the system really decides on its own when there's an unknown new object, how to pick it, and which to pick first, which to pick second, based on how they lie in dependence to each other, if there is space, etc. How this is enabled? So first we have this 3D depth camera on a robotic arm that is taking different pictures of an object. In this case, an object that can be reshaped in any way by a customer. So we also showed this on some fairs. We are triggering then a set of potential grasp candidates that could be potential options to handle this object, to grasp it, to transfer it. And we send this then to a pre-trained neural network to evaluate which of these candidates has the highest likelihood to achieve a successful grasp. This model here is trained actually on virtual data. So we have like 10,000 different objects in the cloud that were labeled with physics simulation on on all kind of different ways you could interact with it, based on the weight distribution, based on the surface, on the curvatures, etc. And then this is projected into the space as if a 3D point cloud camera would see this object. Then the different candidates are basically used, that they were pre-calculated from the physics simulator, are used to train this neural network, which is then able to infer the right decision for unknown objects in the field. On the hardware side, I just shown you the accelerator module. There you can then over gigabit Ethernet vision connect different types of, or USB, different types of cameras, industrial or non-industrial cameras. In this case, RGBD cameras for the depth channel. You can then connect over Profinet different grippers, end effectors, and robots. And with such a small setup of an even letter logic based controller and this accelerator module, you're enabled to do this flexible picking application that I've just shown. And if the moderators can please show the video that I've uploaded, then you can see the application in one of our lab setups. like to thank you and looking forward to your questions in the end of the session.
Thank you, Mr. Claussen, for your presentation. We now listen to Tobias Steege from Fraunhofer IWS. He will talk about how artificial intelligence can be used for material modification with photonic tools. Can't hear you yet. I think now it should be possible.
Can you see my screen?
I can see your screen, but you have to swap the presentation mode.
Okay.
Is there?
Yes.
Mm-hmm.
Thank you, and thank you for this introduction. I would like to speak about laser material modification by laser today, and how machine learning can assist you in this process. But first of all, I would like to introduce myself and the group I work for. I work at Fraunhofer IWS in the group of surface functionalization in Dresden, and together with our colleagues at TU Dresden, we are forming the Center of, the Center for Advanced Microphotonics, which focuses on surface texturing with different technologies like direct laser writing and direct laser interference patterning. And so why is laser surface texturing interesting for a wider audience? This is because you can change with a microstructure the functionality of a surface. For example, the biocompatibility of textured surfaces, which can lead to a better cell attachment, or which you can tailor antibacterial surfaces, which for medical devices to extend the shelf time of a product. And especially the surface rigidity property can be changed by adding a microstructure. For example, anti-icing or self-cleaning as seen here, which is quite interesting for sensors that you can use the sensors in different environments. For example, it's not a sensor, but an airplane being structured by my colleague where there is no ice attaching. It shortens the time before you can fly again in rainy weather. I am part of a European project called Schickard, which tries to get the laser functional texturing to a bigger audience, and this is also why I give this presentation today. We are mainly focusing on the simulation of the laser process and the laser material interaction and the prediction of the surface functionalities. And one of the biggest challenges in laser texturing is the high variety of process parameters which can be changed. And this leads to a necessity that the operator of the machine has quite an extensive know-how about the process and what can be achieved. And also there's normally quite a lot of parameter studies which needs to be done. And we think that there are advanced approaches which can be used to make this process easier. And the question is, can machine learning assist in laser functional texturing and therefore bring you the textures you need for your devices? And one of the most interesting questions is, what should you predict? So should you predict the topography after the laser process, or the surface property from the topography of the sample? And here you have similar inputs like the material, which is the same from both standpoints. But in the laser process, you are working mostly with the input of the machine, which are specific parameters to each laser machine and each laser process. And for the surface property, you work with an topography, which is which are artificial values, for example, the roughness or the uniformity of the surface. And of course, you are interested in the full process chain so that you can predict the surface property from the laser parameters, or to know what the machine can do and which surface properties you can achieve. But if you break up those processes and you predict what happens after the texturing, then you can see if your algorithms work or if your approach is working, and you can also combine those prediction ideas. So the prediction approaches from surface property and laser process. And one good starting point is the prediction of the surface roughness, as this is normally used in the industry to describe a surface, and this is also something where we think machine learning can help. And before I go into detail what I did, I would like to say that I will show you the results of two approaches, quite popular artificial neural networks, and random forest, which is a decision tree based algorithm. And we followed a normal approach. With what you do in machine learning, we gathered the data, and then we did quite a lot of data cleaning. And the question I ask myself is, can machine learning predict the surface roughness via the texturing to help new operators in the machine to know what happens with those specific parameters they are using? And therefore, I set up the experiments together with our partners at George Fisher, and we used two different materials, stainless steel and Starbucks, which are quite common in the industry, and we used one process, which is direct laser writing. And we tried to use all the specific laser parameters which the machine is capable of. So not only to use the parameters which are mostly used, but also to use parameters which are not so common. And here you can see two of those matrices on different materials. On the left side is stainless steel, on the right side is Starbucks, and those matrices are done by the same laser parameters. And you can clearly see that the roughness is different. And on the bottom, you see the analysis of the surface roughness, and the yellow is lower roughness, or a rectangle with a lower roughness value, and the darker parts are higher roughness values. And just to give you an idea how this looks on the surface, on the left side you have a low roughness surface, on the right side you have a high roughness surface. And I'm skipping a lot of steps in between to show you the results. So there was a lot of data cleaning, a lot of data preparation, as we have worked with real data, and we want to know if it is possible to create such networks for the prediction. And here you see on the left side the outcome of the random forest algorithm. On the right side you see the artificial network. And what you see on the y-axis is the prediction of the algorithm, and on the x-axis the real measured surface roughness. And you can see that both have quite a high accuracy, and the neural network goes up to 90%, which is totally enough to make this prediction and help an end user to use this. One interesting thing is that there's a difference in the lower roughness values, but this is mainly to the different initial surface roughnesses of the material, which was lower for Starbucks and higher for stainless steel. And one reason I use two algorithms, and I use the artificial neural network, which is normally used, which is quite popular, and the random forest, is that you can look into the random forest and see which input features have the highest impact on the prediction. And this is called future importance plot, as you can see on the right side. And energy density and pulse energy have the most influence on the roughness, and this is quite normal. And this is not surprising for somebody who works with lasers. I will skip this. I don't have not much time left. So just to show you what I was able to find. So I was able to find, or I was able to create algorithms which go up to a high accuracy, up to 90%. And this will be prime candidates for the Siemens machines to implement. And also I show that I can predict the roughness from the laser parameters. The future importance plots are quite nice to look into the algorithm. And my last thing I would say is that for next I will look in specific roughness parameters which are needed. For example, the peak density, which correlates with the bacterial behavior on different surfaces, or the Wenzel model, which correlates the surface roughness or the increased surface to the contact angle and therefore the self-cleaning of the surface. And thank you for your attention. And if you have any questions, I'm happy to answer them at the end of the session.
Thank you very much, Mr. Steege, for these insights. We are now looking forward to Mr. Gandhi. He is Senior Product Manager at Bosch Sensortec GmbH in Germany and let us know about self-learning sensor and software technology that can be used for sports and lifestyle applications. You have the floor, Mr. Gandhi.
Thank you. Thanks a lot. So I hope you can see my screen.
You can see it fine.
And hear me. Yeah, okay, perfect. All right, so just a brief introduction. So Bosch Sensortec makes a wide variety of sensors, motion sensors, environmental sensors, and also smart sensors, which you see here towards the right. The function that I'm going to talk about or introduce about is a function from one of these smart sensors, as it is focused on edge AI. So typically what happens in these smart sensors is that we focus on improving various aspects of the system. So for example, in reducing the overall system power consumption, in looking at what kind of unique features can our device manufacturers bring to their device, how they can have a scalable solution which fits into wide variety of types of devices, and also how they can get the best quality of data with regards to the sensors. So here what we're looking at is activity tracking system, which is automatic, which is extensible for the makers and also personalized for the users. So this is something that could not be achieved in the past with pre-programmed devices, where users had to manually switch between the different activities, and makers could not extend these devices for additional use cases, or users themselves could not personalize this. So this is what we are solving with by bringing AI directly into the hands of users. So let's take a look at one of the sample problems with this, that comes from the world of fitness tracking. So in fitness tracking, what we see is that there are a wide variety of activities which people do, ranging from CrossFit to home workouts to strength training and yoga and sports, of course, and so on. And for all of these activities, there are very customized special devices, and often which fail because the users themselves do all these activities in a very different way. Second aspect is that there is a very limited availability or supply of coaches who can train the users and who can actually say that, yeah, this is the right way of doing it, or whether you can try this additional exercise or not. And then the third aspect is that there is a lot of manual tracking that is required from the end user side. So in order to address this, we have built a self-learning system which actually learns from the users the way they are doing, or also allows coaches to train this system so that it can continuously track the way users are doing, and also helps in tracking this manually. So now I will request the moderators to actually play the video. Yeah, so thank you. Going back. So this is a brief overview on how do we achieve this actually. So what we do is that we take some sample data, and out of this, using different types of signal processing techniques, we actually generate small fingerprints. These fingerprints are recorded for each of the activities as activity specific patterns, which can then later be integrated inside the sensor itself. So what happens is that because these patterns are integrated inside the sensor, whenever the recognition module inside the sensor sees a similar pattern coming from the sensor data, it is actually able to recognize this right away in terms of the type of activity and also in terms of the number of times this activity was done. Apart from this, what happens is that since the learning itself is embedded inside the sensor, every individual user is actually capable of creating new activity patterns which are similar to the pre-programmed patterns. So this way, this sensor could be 100% customized to the user's activities or their style of doing this specific activity. Similarly, an individual can actually replace or personalize an existing activity to their own activity simply by changing the pattern. So this way, the device is not only used for automatic tracking, but it is also used for learning and personalization. Now for makers, what this brings is that even if they find it later on that, oh, now there is a competitive device which is offering something more unique, something better than what they had originally provided for, these makers can actually create new patterns and update only the pattern over air. So they do not need to modify the hardware. They do not need to modify the original software inside the hardware. They only need to replace the pattern, which is extremely small in comparison to the overall software that is running inside the sensor. This is a brief view on what is the performance of this for different types of activities. What you can see here is learning rate, which ranges from 0 to 1. So we are able to learn all these different types of activities with very high confidence. Typically, learning time is time when a user tries to personalize this activity. So this can be seen in seconds. So in less than 30 seconds, for example, a user can personalize this without spending hours of manual labeling and so on. And at the same time, we have a good recognition rate in terms of F1 score, again, pretty close to 1. So pretty close to 100% of accuracy. The other aspect of performance on the edge with AI systems is how much does it need in terms of power consumption. And here what we can see is that anything in the range of 200 to 300 microamps is actually sufficient from a CPU power perspective. So this actually makes the system highly realistic in building it inside various types of connected devices. So we offer a evaluation system with system that can be connected to smartphones, for example, with fitness trackers and bands, or a system that can also go inside smartwatches directly, so that the user is free from smartphones completely. That's all actually from my side. I mean, here is a quick summary on how this system brings delight to end users. Also would be happy to receive your questions or any comments on this topic.
Thank you very much, Mr. Gandhi.
Yeah.
We have now our next presentation held by Dirk Meyer. He is Department Manager for Distributed Analysis and Control Systems at Fraunhofer IIS, Institute for Adaptive Systems Development. It gives us an insight into artificial intelligence for sustainable and energy-efficient buildings. Here you are, Mr. Meyer. I think you have to put on your mic. Yes.
Yes.
Hear you.
Okay. Now you see my screen or not?
Yes, also we do.
Okay, great. So I'll start my presentation, keep it quick. On the last one for the break, I guess. Yeah, so a bit completely different topic now, energy efficiency in buildings, but it's quite a relevant topic, which you all might know, because buildings are one of the major contributor to the global consumption of primary energy sources, and are of course a contributor to emissions as well. We have quite ambitious goals, the zero emission building in 2050. And as you can see on the right-hand side, we're quite far away. So there's quite a long way to go. And now let's see whether perhaps artificial intelligence can help us to reach those goals. So the situation is as follows. Future or even modern, let's say modern building energy systems are quite complex systems. You have multiple energy sources, renewable sources, maybe photovoltaic cells on your roof. You have heat pumps in the cellar of your house. Sectors are coupled, which means your heating also produces electricity or vice versa. And you also have new sinks for electrical energy, like that you have to refill your car in front of your house every evening. In parallel, we not only have, let's say, an energy network for heating, ventilation, cooling, and energy, we also have an information network in buildings, which gives us opportunity to build up an IoT network of smart devices and to integrate artificial intelligence into buildings in order to enable an improved security of supply, improve the healthiness of the environment, reduce emissions, of course, and also gather economical benefits. So the main fields that we were working on in the last years were the following. First field is to improve digitalization in the model-based design and doing feasibility analysis to optimize energy concepts in a very early design phase. Something like model-based design, which is standard for electronic systems for, I guess, 50 years or so, should now come also to building energy systems. And a bit more going into the operation stage of a building, automated analysis of operation data, so big data analysis. If you have a big building like an airport or a shopping mall or a production plant, you have lots of sensors gathering a high amount of information that you cannot analyze by hand anymore. And even more, even nowadays, building energy systems are programmed by hand, and it's a quite complex task that is always faulty. Not any building energy system that is designed for, let's say, a bigger building is 100% fault-free. So data analysis for fault detection and correction of those faults is quite helpful. Next stage would be something like condition monitoring and forecasting. We all know condition monitoring from the world of Industry 4.0, but as we will see on a later slide, condition monitoring is also quite useful for building energy systems. And last but not least, let's say the core of artificial intelligence, the gold standard is model predictive control and intelligent energy distribution, which I will present now on the next two slides. Quite simple example of a, let's say, complex energy system. We have here the photovoltaic cell and here a heat pump, and we have two storages and two rooms that we want to heat. And now we need some intelligent energy distribution management in order to balance this source, and store energy when it's not available from the sun and so on. What we tested is a rule-based agent that you can train by reinforcement learning. It's a classical training schedule from the early days of artificial intelligence. And model predictive control, which is from the chemical plant engineering from the 1990s, where we use genetic optimization to balance all those complex goals that such an energy system tries to find a compromise for. I will show you on the next slide a result, but just giving a brief overview. What's the difference between those schedules? It's the rule-based agent is quite simple. It's just turning on and off the different sources and sinks. You need a simple model of your energy system. The whole algorithm is of medium complexity, and it's meant to learn offline in the design stage of your energy system, while model predictive control is an online scheme. But what it actually does is doing an optimization in every time step. So you need a powerful computer in your building energy system, and you need a quite precise model of your energy system. So we did a simulation for both cases, and what we found out is, of course, the model predictive control is quite more effective compared to the reinforcement learning of the agent, the rule-based agent. But as said before, it's of higher complexity. But both are outperforming the traditional conventional automation systems. This is the good news. So what we now try to find out is what would be the next step for a applicable building energy system. Because when you're seeing what's actually mounted into buildings, what's actually installed, they're quite far away from using something like model predictive control in most cases. So maybe something like rule-based reinforcement learning. It's not, let's say, the gold standard of artificial intelligence, but it still helps you to save energy with a more simple solution. While model predictive control might be something that would be good for quite complex energy systems when you have a real high energy bill every year, and it turns out that even an investment of 10,000 euros or more could be helpful to save energy in the end after 2 years or so. Okay, second and last example, as I promised, prognostic tool for energy systems. As you see, in every HVAC system, we have something like a filter system, of course. And what we implemented in an example at the real building is predictive maintenance for filter systems, which can be helpful, of course, to save energy, because when the filter load gets higher, the electric energy for pumping air through the filter increases. Also, by optimizing maintenance schedules, you can save material, filter material. But it's also important for future applications, like a healthy indoor environment. In the keynote lecture this morning, we saw ideas for getting viruses out of the building by clever HVAC solutions, and this could be a future research direction for future building energy systems, not only saving energy but also improving the healthiness of the indoor environment. Then, of course, wireless automation networks. Getting more sensor data allows you to improve the precision of your control system. Then, not shown, but it's important, model-based system design. I already pointed out that it's quite a task, quite an issue, to transfer all those things that are standard in the aeronautics, in the design of electronic circuits towards building energy systems. Then, maybe for smart systems here in this community, very interesting, using smart sensors and edge AI in every device to make every energy source, every energy storage its own agent with its own intelligence, in order to get to something like a distributed and scalable AI system. So bringing more sensors into a building by something like a plug-and-play solution, with a final goal to have something like a resilient energy system, where you can also withstand something like a catastrophe when the energy supply from outside breaks down, or even you don't need the energy supply from outside, because then it's a pure zero emission building in the end. Yeah, okay, so that was a brief overview about what could be done with artificial intelligence on the edge in building energy systems. Thanks.
Thank you for this overview, Mr. Meyer. We are now answering all your questions. I would like to ask all the speakers of this session to turn on your cameras, and I hand over to Mr. Karmann.
Thank you for the introduction, Evelyn. Waiting a minute until all appear. We had not so many questions, but I think I selected one interesting for any of you. And for Heiko Claussen, I'm very eager to ask my own question, sorry, since later on we have a workshop where I myself am talking about autonomous operation of machines. So I wanted to ask you, Heiko, when are robots working really autonomous? Or do we never achieve it and have to describe them as extremely high automated, how high they are automated at all?
That's a great question. So as head of autonomous machines at Siemens, I'm actually working exactly on this vision. And we actually have applications in the real plant where we enable autonomy already now. So we are in the first steps developing in this direction. And yeah, our vision of autonomy is that you don't have to program anymore yourself, but that the machine is automatically generating its program by, for example, design data. So we have applications in our factories where the digital twin of the design of the product is actually used to automatically generate the code for this application to be, for example, manufactured. And this enables you then to create low lot size products. So you can, at an affordable cost, build every product differently. We have that, for example, for cabinets, electric cabinet assembly, where we have in our factories like a lot size of 1.3, and only such autonomous systems that are enabled by artificial intelligence are able to solve such problems today.
Okay, yes, I see. Thank you, Heiko. Then second speaker, I think, was Tobias Steege. For you, I have a not so, but I will not comment. I just give the answer. If you already know parameters to achieve flat surfaces without roughness, what do you need the AI for? That pulse energy and energy density have the most dominant influence of roughness was known long before AI was introduced. Seems to be an expert on surface treatment. Can you answer that?
Yes, of course, and thank you for this question. Yes, wonderful. And yes, it is true. And somebody who works with lasers for a long time knows all this and knows which parameters should be used. But the goal is to make this easier for new users and to reduce the training time on the machine, and therefore such prediction algorithms can be used to give an idea of what happens. So you can do this without the machine or before you structure.
Okay, so are you in contact with the companies who sells the lasers to give them something like a program how to use the laser? I remember when I was buying a deep etching machine one time, I got a Bosch process added, so I knew how to use that machine for a certain purpose. Is that your idea too?
Yes, so we are working with different companies, and normally we help them to get their machines better. So we normally do the research for them, and then they implement those in their machines.
Okay, thank you, Tobias. Then I scroll down. Okay, for Kaustubh Gandhi, is it correct that the sensor is learning the general movement correlated to a specific training unit? Why is it not necessary that the sensor learns the individual movement patterns of an individual training person? Do you understand the question?
Yeah. Yes. So in general, there is a dilemma about would the user be interested in doing the right way of doing things, of doing an activity, or would the user be more interested in his or her personal way of doing things?
Yeah. Okay.
So the sensor
So that's
can be
exactly
configured.
the background of the question. You think? Okay.
Yes.
Okay.
Yes. I think so. I mean, this is the closest match as I see. So the sensor can be configured to a personal style or a standard style. So
Okay.
when Bosch offers this sensor, we offer 15 standard styles. And we say that even OEMs or makers can create their own standard styles. So saying that this is this Olympic standard, or this is the gold standard, and so on. And then individuals, of course, they need certain levels to go through. So they can say that, no, I'm at a beginner level right now. I need something simpler. I need something to get still motivated. They can have a simpler style. And when they go to a slightly professional level, then they can aim for the Olympic standard or something like this. So this way they can actually.
Okay.
Yeah.
That's a great answer. It reminds me on my chess computer. I would start at a very low level and increase it afterwards. So it works the same way?
Yeah. Yes,
okay,
yes, absolutely. Yes.
So,
Yes.
not bad, that question. Okay.
Yeah.
Then I was not sure. Dirk, did you talk about energy efficient buildings?
Yes.
Okay, high energy. It starts with a not with a question, but with an idea. I think high energy efficient buildings can be reached without artificial intelligence at all, just by the use of constructive means and material selection. Okay, what can the AI put on top?
Yeah.
Sorry.
No,
There comes another
no.
question.
No,
Yeah.
I just skipped this information in the talk.
Okay.
That's true. You can use better construction or anything in order to save energy. That's a clear fact.
Okay.
But if you consider a modern building and you consider the thickness of this foam on modern buildings, there is, let's say, the development has come to an end. And now you have 30 centimeters or something on the outside of the building, which is more than enough. Let's say, if you have ever bought a window, real window for a house, and you try out to lift it, it's 3 layers of glass in modern buildings. You cannot move it alone. So saving energy alone by constructive means is, let's say, it has come to an end. That's the first thing. And the second thing is what I pointed out: the complexity of the energy system. In order to reach out towards a zero-emission building, you have to orchestrate all those sources like photovoltaic cells, solar thermal cells, heat pumps, and so on. And for, let's say, for a little house for one family or so, you can try to turn the knobs by yourself. But if you think about larger building, office building or so, then it's important. Then it's impossible to do it by hand. You need some clever control.
I hope that answer is enough for the questioner. We got one just in now for Gandhi again. I missed which was the size of the sensor system and how much did its footprint increase by adding the edge IA layer? Okay.
Okay.
Yeah. They are really experts in the session now.
Yeah. Yeah. So you can imagine that these are MEMS sensors. So MEMS sensors are typically of the size 3 millimeter by 3 millimeter. They are really tiny. They are designed for smart watches, also in-ear devices and such tiny devices, apart from smartphones and so on. So I mean, adding edge AI here actually meant adding a slightly powerful microcontroller to the system, and this did not act, since we have a system in package, this actually did not impact much on the size. It more work was had been on to how we can really bring the overall system in in such a small microcontroller that it can still execute, it can still learn from the data that is coming in, and so on. So the overall size still is in the range of 3 by 4 millimeters. I hope this answers your question.
Okay, I hope so too, since we are close to the end. But I myself was asking if we need special hardware for solving edge AI questions. But I think, okay, we are coming from EPoSS community, so we are building hardware. But I think we have to discuss that on a different place, since I was shown that our time is over. It's a quarter past. So thank you for your contributions, and thank you to the audience for your interesting questions.
Thank you. Thanks a lot. Okay.
Thank you to all the panelists. Thanks for your questions and the attention. Before we will have a break, I would like to draw your attention to 3 webinars on AI at the Edge, organized by the Knowledge Transfer Network KTN in cooperation with EPoSS. They will take place on the 9th of October for digital industry, on the 13th of November for mobility, and the 11th of December for healthcare. The registration for the webinars is already open. You can see the register link directly in the chat box. After the break, we would like to welcome you to our 5E Transversal workshop, which will be moderated by Petra Weiler and Nicola Goose. Both are colleagues of mine at VDI IT and coordinators of the 5E project. We will start with a workshop at 5 p.m. and it will take 1.5 hours till 6:30. Petra will now say a few words about the following workshop.
Thank you, Evelyn. My task to give a short motivational teaser to all of you to make sure that you stay with us until 6:30 tonight. We will have an exciting mixture between you can only listen in to some presentations and participate as a more passive attendant, but we also have on the other hand, some active engagement where you can be online and you can interact with us through an online survey and in that participate and experiment. Actually, I think this workshop is as unpredictable as it will get during these 2 days because nothing is predefined in the answers that you will give, and please be sure to participate for these 1.5 hours this evening, and you will get, those who stay, of course, will get the results in a summary after the workshop. Thanks a lot, and meet you tonight.
Thank you for this preview, Petra. So for me, it's time to say goodbye for today. Thank you for attending our first day of the EPoSS and EPSI annual forum. And thank you all for great presentations and interesting questions. I wish you an inspiring workshop with Petra Weiler and Nicola Goose. And we'll hear each other again tomorrow at 10 a.m. Central European Time for the second day of our annual forum. Goodbye.